Welcome back to the Deep Dive. Today we are soaring into the really crucial world of advanced manufacturing. We're looking at the materials that make high-performance engineering possible. Think fighter jets, high-speed rails, all that next-gen stuff.
Right. We're talking about fiber-reinforced polymer composites, or laminates for short.
And these things are built layer by tiny layer.
Exactly. And traditionally, creating them, it's a process called sintering, is just agonizingly slow. And very expensive.
It delivers great quality, I assume.
Oh, impeccable quality. The polymer chains have all the time in the world to diffuse and bond together. But in an industry like aerospace, time is, well, it's literally money.
So the goal is always speed. And the technology everyone's looking at for that is something called ultrasonic consolidation, UC.
It promises to weld these layers together in like milliseconds using friction and heat.
But here's the hook for our deep dive today. UC is, well, it's a pretty chaotic process.
It is. It's ultra fast, the heating rates are insane, and all the energy is coming from one side, from a tool called the sonotrode.
And that combination makes getting a high-quality, defect-free structure incredibly challenging.
And we're focusing on a really high-end material today. PKCF prepregs. That's polyetheretherketone, a tough polymer, reinforced with carbon fiber.
And the number one measure of quality of whether these layers are actually stuck together is the interlaminar shear strength.
Which we'll just call ILSS to make it easier.
Okay, ILS it is. And here's where things get really interesting. Conventionally, manufacturers use a little trick when they're welding these layers.
They do. They insert a thin, kind of sacrificial layer. It's called an energy director, or ED.
It's supposed to be a helper, like a fuse that melts first to get the whole bonding process started.
That's the theory. It's just a thin film of the pure polymer, the PEEK. The idea is that this little film will melt really fast and create this perfect, smooth diffusion layer between the tough carbon fiber sheets.
So our mission today is to really dig into that convention. Does this energy director, this supposedly helpful tool, actually improve the quality and the strength of the final part?
And if it doesn't, what's the best way to do it? What's the optimal processing time for this rapid welding technique without any help?
Okay, let's unpack this, because it seems like the traditional wisdom here might be leading manufacturers down a much weaker path. So to understand the materials, what did the researchers actually work with here?
Well, they used commercially available PKCF prepregs. These are, the strong carbon fiber reinforced layers.
And they set up a direct comparison.
Right. They needed to compare apples to apples, so they carefully stacked the layers to make sure the final thickness would be similar for the mechanical tests.
So one set used these prepregs with the energy director films sandwiched between every single layer.
And the other set was just the prepregs themselves. No helper film, just consolidated together.
So with ultrasonic consolidation, the main thing you're controlling is the energy input, which basically means time. But before we get to the results, let's quickly walk through how the energy transfer actually works. I think this is crucial to understanding why things might fail.
It is. The process is quick, but it has very defined stages. First, the sonotrode presses down with a set amount of force.
Okay.
Second, the ultrasonic vibrations start, and this is where the heat comes from. But there are two different heating mechanisms happening.
And this is the part we really need to pay attention to.
Yes. Initially, you get what's called surface friction heating. This is just the layers rubbing against each other under pressure.
Yeah.
It's relatively slow, kind of superficial.
But that's not where the real speed comes from.
No. Very quickly, as the polymer starts to soften, you transition into viscoelastic heating. This is internal heat generation, and it's incredibly fast. The polymer itself absorbs the vibration and dissipates it as heat through its entire volume.
So that's the key to UC's speed, that rapid transition. But it's also the risk, right? If you stay in that high-speed phase for too long, you can just cook the material.
Precisely. You risk overheating and serious structural damage. And that brings us to the main variable they tested, the ultrasonic duration, or 2 years.
And what were the timings?
They tested a range. They started at 600 milliseconds, went up to 800, and then all the way to 1200 milliseconds.
Just over a second.
Right. And those few milliseconds control how deep into that potentially destructive, super fast heating phase you're driving the material.
So the big question is how that duration, especially with and without that energy director film, physically changes the final structure. This is where we stop talking theory and look at the evidence.
And this is where the results really start to get counterintuitive. Let's start with just the physical thinning of the laminate.
Okay, so when the layers melt, the material squeezes out, so you'd expect it to get thinner.
You would. And for the samples with the energy directors, the thinning was pretty linear. More time meant more melting, more thinning. Simple. At 1200 milliseconds, they saw a good amount of thinning.
But the results without the energy director were completely different.
Totally different. They followed a distinct S-shaped pattern. The thinning actually maximized really quickly, right around that 800 millisecond mark.
And then what happened?
Then, if they pushed the time longer to 1200, the thinning actually decreased a tiny bit.
That suggests something is happening there.
It suggests that 800 milliseconds is the sweet spot. It's the optimal point for material flow and compaction before the heat starts doing more harm than good.
So getting rid of the ED seems to force the material to find its optimal melt point much faster. But what about the internal structure? You can't see that from the outside.
No, thinning doesn't tell the whole story. And the microscopic view. This is where you see the paradox in action.
What did they find?
Without the energy directors, the final structure was, frankly, beautiful. Uniform, robust, almost completely defect-free.
Really?
Yes. The original interfaces between the layers, which you still kind of see at 600 milliseconds, had completely blurred and vanished by 1200. It showed perfect, homogeneous polymer mixing.
And the samples that were supposed to be helped by the energy director?
A total mess. Total non-uniformity. We're talking layer curvature, big voids, and even signs of localized failure. Especially at those longer times. 800 and 1200 milliseconds.
So this is where the ED fails spectacularly.
It does.
But why? I mean, if it's designed to melt first, why is it causing all these structural problems?
Because it melts too well. It's too aggressive.
Ah.
Think of the ED like a layer of hot glue that just melts instantly and spreads out way faster than the stiff prepreg layers can even conform.
So it's creating chaos.
It creates chaos, it spreads, it gets squeezed out, but in the process, it overpressurizes and physically damages the neighboring prepregs. The ED actually ends up acting as a damper during the initial heating, and then it turns into a destructive force.
Wow. And the analysis showed something really bizarre, didn't it? The prepreg layers themselves. They actually got thicker.
They did. For the ED samples, the prepregnancies actually increased as the time went on.
That's the smoking gun right there.
It is. It's the visual proof that the molten polymer from the ED was being pumped or forced into the prepreg layers. Instead of making a nice clean bond on the surface, it was pushing the structural layers apart from the inside, causing internal damage and weakening the whole thing.
So if the structure is that defective, the mechanical performance has to follow. This brings us to the moment of truth, the ILSS data, the actual strength numbers.
And they showed two completely opposing trends. It was really stark.
Let's start with the good news, the laminates without the EDs.
For those, the strength just kept getting better. The ILSS increased continuously with the duration, and it peaked at a high of about 60 MPa at the longest time, 1200 milliseconds.
So longer time equals stronger bond. That sounds like a clear winner. 60 MPa is an excellent number.
It sounds great. Until you look at the ED results.
Uh-oh.
Their ILSS peaked much earlier and much lower. It hit about 40 MPa at 800 milliseconds. But here's the kicker. When they pushed the time to 1200 milliseconds, the ILSS crashed.
It went down.
It crashed down to about 30 MPa. The structure was so defective at that point that the extra energy was actively destroying the bond.
And that 30 MPa, that's directly linked to those delaminations caused by the overly aggressive energy director.
Absolutely. The fracture analysis confirmed it. In the ED samples, the crack always ran right along the interface between the prepreg and that weak ED film.
And for the no ED samples?
A different story. Especially at 800 and 1200 milliseconds, they showed these branched crack patterns. It meant the bond was so strong the crack had to really fight its way through the structure instead of just zipping along a weak layer.
So this raises a really important, almost non-technical question. You have a high strength point. 60 MPa at 1200 milliseconds, no ED. Why wasn't that just declared the best outcome? If strength is the goal, why settle for less?
Because in engineering, reliability and structural integrity, they outweigh pure strength if that strength comes at a hidden cost. The researchers specifically rejected that 60 MPa value because achieving it at 1200 milliseconds required so much energy, so much melting, that it was causing microscopic damage to the original carbon fiber structures.
So you were getting a strong joint, but you were weakening the composite overall. You were masking damage with a high strength number.
Exactly. The real aha moment isn't finding the highest number, it's finding the most rational choice.
And that was?
The most rational defect mitigating choice was 800 milliseconds without the energy director. That duration gave them an impressive ILSS of over 50 MPa, while drastically minimizing the damaging effects of the vibration and keeping the structure uniform. It's the optimal balance of speed, strength, and integrity.
So what does this tell us about the future of this rapid manufacturing technique? The final synthesis is pretty much a clear rejection of these conventional aids.
Absolutely. The takeaway is that the approach without the energy director is recommended for making these PTCF laminates.
And the numbers really back that up.
They do. At that rational duration, 800 milliseconds, the ILSS they got without the ED was over 50 MPa. That exceeded the absolute best number they got with the ED, that 40 MPa, by a solid 25%.
So you add the helper and you weaken the final product by a quarter.
A very powerful lesson in unintended consequences.
It is. But we have to put this in context. How does this optimized UC method stack up against the traditional super slow methods?
Well, it's competitive, but it's not yet superior in pure strength. UC offers these huge speed advantages, but the ILSS values they achieved are still about 40% lower than what you get from traditional thermoforming,
where the material has hours to diffuse perfectly.
Right. But they are matching up really well against other cutting-edge rapid techniques.
Such as?
Well, this optimized UC process is only about 10 to 25% less strong than results from things like laser automated fiber placement for similar materials. And given that UC is arguably faster and less complex, that's a very promising benchmark.
And they held some important variables constant, like the amplitude of the vibrations. So what does future optimization look like?
The path forward is pretty clear. They need to start pulling the levers they didn't touch in this study. They kept the vibration amplitude fairly low.
And other research has pushed that further.
Well, yeah. Other research has shown that if you increase the amplitude significantly, sometimes up to 80 micrometers, it can fundamentally change the heating dynamics. You could potentially get even shorter processing times and still maintain quality.
Or adjusting the geometry of the energy source itself.
Exactly. Decreasing the sonotrode area could lead to more uniform energy transfer into those fusion zones. That should help spread the heat more evenly and maybe even eliminate the localized damage they saw at that 1200 millisecond mark.
This has been a truly fascinating deep dive into a manufacturing paradox. The key takeaway for anyone building these high-stakes components is that sometimes removing the traditional complexity actually gives you a stronger, more reliable, and faster product.
A cleaner, shorter, and stronger approach. 800 milliseconds without the conventional energy director gave them an ILSS over 50 MPa.
And we saw that the strength of that bond really hinges on that extremely fast transition from slow surface friction heating to that deep, intense viscoelastic heating.
Right, that 800 millisecond sweet spot is all about balancing the speed you need against the damage you cause by overheating in that intense phase.
So here's a provocative thought for you to chew on. If the ultimate goal of ultrasonic consolidation is maximizing quality at maximum speed, future research can't just focus on the total time that you stop. They need to figure out how to precisely control the rate of that energy input, the exact transition point between the slow friction heating and the super fast viscoelastic heating.
Getting the perfect level of melt and flow without a single moment of damaging overdrive.
Exactly. That kind of precision control is what separates the current benchmark from the truly perfect composite joint.